This is a recording about Norton equivalent circuits. These are used as an alternative to Thevenin equivalent circuits. They were invented by Edward Lowry Norton, an American. If we consider on the left a Thevenin equivalent circuit, I've drawn a simple constant voltage generator and series resistor, that is the internal resistance, connected to load terminals A and B. I want to calculate the current in that circuit. The load current in the circuit is simply going to be the source divided by the sum of the resistance in the circuit. On the right hand side, on this circuit, a short circuit has been applied to the load terminals A and B, and the short circuit current is simply given by E over R. On the left hand side, if I were to divide top and bottom of that equation by by R, I would have E over R divided by R plus RL over R. That amounts to E over R times R over R plus RL. And of course the E over R term is the same as the short circuit current. So this now looks like that situation. This particular expression is seen when we are sharing current between two resistors. One labelled R and the other labelled RL. The incoming current being shared is ISC, and the load current is the current that flows in RL. So in this situation, it appears like a source of current has been shared between two resistors. This is the principle of the Thevenin equivalent circuit. The Norton equivalent circuit. A Norton circuit contains a constant current generator and a parallel resistor, looking like that. A load is connected to the circuit called RL. The constant current generator has two properties. Fairly obviously, it always produces the same current, and more importantly, it has infinite internal resistance. So unlike the constant voltage generator, which has zero internal resistance, this has infinite internal resistance. This can be symbolized by thinking about the two symbols used. With a constant voltage generator, it looks like a closed switch. Some sort of switch that is closed. Whereas this symbol just here, which is the constant current generator, actually looks like some sort of open switch. So the implication is the left hand side switch over here has zero internal resistance, whereas over here this switch has infinite internal resistance. That helps us remember the two properties. It's easy to convert from a Thevenin circuit to a Norton circuit, and vice versa. Looking at the circuit at the top of the page, you'll see it has a 2 ohm internal resistance and a 10 volt constant voltage generator. If I want to convert that into a Norton equivalent circuit, all I do is put a short down here and measure the short circuit current. ISC, what current will flow. Sometimes that's also symbolised by using an ammeter as a short, because that will show the short circuit current. Well, fairly obviously, ISC is going to be E over R, or 10 volts over 2 ohms, which is 5 amps. The internal resistance is of course the same. So my new circuit will have a 5 amp generator and the same resistance, a 2 ohm internal resistance. And that will replace the original circuit and act in the same way, producing the same current in the same load. For the Norton circuit shown below, we can convert that to a Thevenin circuit simply by measuring the EMF that appears at the terminals of the circuit. All the current from the constant current generator must pass around that loop if no load is connected. So the E value will simply be the 4 amps times the 8 ohms, giving me 32 volts. So my equivalent circuit will look like this, with a 32 volt generator and the same internal resistance, 8 ohms. Again, these two are equivalent to each other, each producing the same current in the same load. One type of circuit is used in one situation and the other type in a different situation. So for instance, in transistor equivalent circuits, we commonly find that current generators are used. The actual theorem looks like this. The current which flows in any branch of a circuit is the same as that which would flow in the branch if it were connected across a source of electrical energy, the short circuit current of which is equal to that current which would flow in a short circuit across the branch, and the internal resistance of which is equal to that resistance appearing across the open circuited branch terminals. This is a fairly dense paragraph. This can be reduced to two particular rules which enable us to convert the circuits. So for instance, these two rules there: remove a load and measure the short circuit current, and with the load removed, remove the short circuit, replace the generator with its internal resistance, and then measure the resistance at the load terminals. So these two rules will help us produce a Norton equivalent circuit. So if I look at this example on here, this is the one used for the Thevenin equivalent circuit, and we'll work our way through this. The original circuit is shown just here with a load on it. So we're going to apply the rules we just saw. We're going to apply rule 1, which says take off the load and then measure the short circuit current. So here we've got an ammeter shown recording current as if it were a short circuit on the terminals. So when you short these two terminals together, effectively you're shorting out that 5 ohm resistor. So that 5 ohm resistor actually is not significant now and doesn't take any part in that calculation. So the short circuit current is simply going to be the 10 volts divided by the resistance in the loop, which is the 2 ohm and the 3 ohm, which gives me 5 ohms. That therefore gives me 2 amps. So my new generator will have a value of 2 amps. Thinking about rule 2, rule 2 says, again with a load removed, replace any generator with its internal resistance. A constant voltage generator has 0 internal resistance, so that will just produce a link in there with no generator symbol shown. Now imagine we're measuring the resistance at those terminals using an ohm meter, and that's going to produce a resistance of 5 ohms here, and in parallel with that there is another 5 ohms made up of the 2 and the 3. 2 5s in parallel give me 2.5 ohms, so this resistor over here must be 2.5 ohms. So that is a new equivalent circuit that produces the same current in the same load as the original circuit. And if you recall, the load current we worked out in the Thevenin circuit was 1 amp, and in here again I've got a constant current generator sharing current between two components, both of the same value. So therefore there must be 1 amp flowing through the load, which is the same result we had in the Thevenin equivalent circuit example. Let's look at another example. This is one with a constant current generator in it. Same idea applies. We take off the load, we apply rule 1 and put a short up the terminals here. So the load removed, there are only two paths for the current. One is down the 6 ohm resistor, other is through the 3 ohm resistor. We want the current through the 3 ohm resistor, so we're going to have to share some current there. So let's do a sharing. 12 amps shared between a 3 and a 6. I want the current in the 3 ohm resistor, so I put the 6 ohm on top. That's 12 amps, and we're taking 2/3 of 12 amps, or 8 amps. So my new generator is 8 amps. Over here, we, again with the load removed, we replace the generator, a constant current generator, with this internal resistance, which is infinite, so that's an open circuit. So when I measure the resistance here, I'm seeing effectively two resistors in series, the 6 and the 3, making 9 ohms. So in this circuit, my resultant value must be 9 ohms. So that's my equivalent circuit. This is a slightly harder one to finish with. In this circuit, we have 3 resistors in here, slightly more than before. So we're going to start off applying the rules. The load has to come off for both rules. So looking at rule 1, when we take the load off and we put a short circuit on here, it shorts out this 50 ohm resistor just there. So the current from the generator, the 10 amps, is being shared between the 20 and the 30. So sharing again, 10 amps shared between 20 and 30. I want the current passing through the 30 ohm resistor, so I put the 20 on top. 20 over 50 is 0.4, 10 times 0.4 is 4 amps. So that's a 4 amp constant current generator. So let's put that in our equivalent circuit down here. It's going to be 4 amps. Looking at the internal resistance then, again, with the generator replaced with its internal resistance, which is infinite, an open circuit, and we measure with an ohm meter at the load terminals, we will see a 50 ohm resistor there, in parallel with which are 2 series resistors of 50 ohms. 50 and 50 in parallel make 25 ohms. So my new resistor down here must be a 25 ohm resistor. So that's a slightly harder example with more components in it, but the principle is the same every time. Take off the load, record the short circuit current at the terminals, and then take off the load again and remove the constant current generator, replace it with an open circuit, and measure the resistance at the terminals. And that concludes the recording.